In 1300, an entire guild was chartered to manage one material. Most modern kitchens throw straight in the trash. That same waste can outshine candles for months at zero cost, but only if you understand what makes it dangerous. The Tallow Chandlers Company regulated this animal fat economy for centuries, overseeing a basic domestic fuel network. Before electricity, 18th and 19th century households hoarded cooking grease as primary infrastructure, repeatedly dipping cotton wicks into rendered tallow to keep their homes lit. It was smoky and pungent, but it worked. The Huntington Library archives record how early families relied on iron Betty lamps to burn everyday kitchen fats. During World War II, governments revived this thrift, launching salvage campaigns that redirected grease from frying pans to military supply lines. Today, modern homesteaders are turning back to these exact techniques, testing whether this historical logic still holds up for off-grid survival. Translating historical thrift into modern practice requires a strict boundary between resourcefulness and recklessness. Open flames are inherently hazardous. National Fire Protection Association data shows that candles ignite over 7,000 home structure fires annually, causing dozens of deaths. Improvised liquid fuel lamps carry similar risks of fuel spillage and glass breakage. Because of these hazards, local municipal codes strictly regulate open flames in residential areas, with New York City and Baltimore County restricting unapproved lamps in multi-unit buildings. Responsible sourcing is also necessary. This method relies strictly on personal kitchen waste or legally permitted byproducts, never unauthorized commercial scavenging. Safe operation requires constant supervision, stable, non-combustible surfaces, correct wick selection, and active room ventilation. Treat these setups as temporary emergency utilities, not as casual household toys. Converting raw kitchen waste into a stable fuel requires separating usable fats from water and organic debris, the main challenge in making these byproducts burnable. For raw animal fat, this means rendering. Heating the fat to 230 degrees Fahrenheit or 110 degrees Celsius begins the purification. A gentle simmer allows trapped moisture to escape as steam, while the clean, liquefied tallow separates from the solid tissue. For low-tech alternatives, households can render fat in an oven at 180 degrees Fahrenheit for 8 to 12 hours, or use a slow cooker on the low setting for 8 hours. Pouring the hot liquid through cheesecloth or a fine mesh filter strains out the remaining solids. Used cooking oil requires a similar clarification, passing through paper filters to catch microscopic food crumbs that would disrupt combustion. The quality of this filtration directly affects how reliably the oil behaves as fuel, leaving a stable source ready for clean storage. Once clarified, these liquids transition from waste into predictable resources. Every liquid fuel lamp relies on three elements: a reservoir, a wick, and an air supply. Inside a glass jar, the clarified fat functions as a fuel source, but it cannot burn in bulk. Instead, capillary action pulls the liquid upward through the microscopic channels of a cotton wick. This physical process succeeds only when the rate of fuel delivery matches the demands of the flame. If the wick is too thick, it draws more fuel than the heat can cleanly consume, producing heavy soot and unstable flickering. If the wick is too thin, the flame starves and dies. Because animal fats and vegetable oils are highly viscous, they flow more slowly than refined petroleum. Natural fiber wicks, like a braided cotton cord, handle this thick consistency far better than synthetic alternatives. Sized correctly, a central cotton wick suspended in a glass jar creates a balanced system, keeping the flame steady while the vessel provides a stable, heat-resistant base. A live burn test using a calibrated digital lux meter and carbon monoxide monitor establishes the exact performance of this salvaged fuel setup. While a standard candle averages just 13 lumens of light, the clarified oil lamp reaches 30 lumens in controlled conditions. Historic data from the EXARC database confirms this output remains steady, lasting over 4 hours on just 30 milliliters of fuel. However, clean combustion relies entirely on airflow. Without active room ventilation, fine particulate emissions quickly exceed safe thresholds of 35 micrograms per cubic meter, proving that utility must always be balanced with indoor air safety. Wood ash, often thrown out as useless dirt, serves as a rich source of potassium carbonate. Leaching clean, untreated wood ash in water extracts this alkali, creating a raw lye solution. When mixed with rendered kitchen fats, a chemical reaction called saponification occurs, binding the ingredients and turning them into soap. Because of the highly corrosive nature of this reaction, handling lye requires safety goggles, chemical-resistant gloves, and outdoor ventilation. The freshly poured soap is not ready for immediate use. It must cure for 4 to 6 weeks to allow excess water to evaporate, ensuring a safe, skin-friendly bar. True resilience isn't bought, it is salvaged. As modern systems grow fragile, our ultimate safety net remains hidden in our own kitchens. Share your thoughts below.